A 17.2-kilometer bridge costing over $1.1 billion spans the vast Tagus River, where fierce winds, weak soil, and constant earthquake risks are always present. But how was it built? How can a structure curved to match the Earth's own curvature still stand firm under enormous loads? And what transformed Lisbon from a major traffic bottleneck into a strategic logistics hub for the entire nation? This is not just a bridge, it is an infrastructure revolution. Watch until the end to discover how they achieved the seemingly impossible. Vasco da Gama Bridge is one of the most important transportation infrastructure projects in Portugal, built to address the severe congestion crisis in the Lisbon area at the end of the 20th century. Before this project began, nearly all traffic crossing the Tagus River depended on the 25 de April bridge, causing prolonged traffic jams that directly affected freight transport, urban connectivity, and regional economic growth. In this context, the Portuguese government decided to invest in the construction of a new large-scale bridge to create an alternative transport corridor and expand connection capacity. The project was carried out under a public-private partnership model with a total investment of approximately $1.1 billion. Construction began in 1995 and was completed in 1998, coinciding with the 500th anniversary of Vasco da Gama's voyage. With a total length of about 17.2 kilometers, it is currently the longest bridge in Europe. The bridge spans the Tagus estuary, connecting the northern and eastern parts of Lisbon, while also opening new development opportunities for the suburban region. From an engineering perspective, Vasco da Gama Bridge is a complex structural system consisting of a cable-stayed bridge in the main span area and a multi-span girder bridge system along the viaduct sections. The overall design was optimized to meet the region's unique natural conditions, including weak soil tidal influence, strong winds, and earthquake risk. The construction process began with foundation treatment under highly complex geological conditions. Large diameter steel casings were driven into the riverbed combined with board pile systems to create a stable foundation. Concrete was poured underwater through tremier pipes, ensuring structural quality and consistency. After the foundations were completed, the bridge piers were constructed using a segmental concrete pouring method. A climbing formwork system was used to raise the pier shafts layer by layer, ensuring precision and structural continuity. In the main span area, the large piers were specially reinforced to withstand greater loads and serve as support points for the cable-stayed towers. The two bridge towers were built using a similar method with significant height and a gradually tapered vertical shape. Once the towers were completed, the cable system was installed step by step. Each cable strand was pulled, anchored, and tensioned using hydraulic equipment, forming the main load-bearing structure of the bridge span. At the same time, the bridge deck segments in the main span were constructed using the balanced cantilever method. Each concrete segment was installed from both sides of the tower, maintaining load balance throughout the construction process. When the two cantilever arms met at the center, the closure segment was completed with extremely high precision, finalizing the main span structure. For the viaduct sections, pre-stressed concrete girders were pre-cast in a casting yard and then transported by barge to the installation site. The girders were lifted onto the piers by cranes and connected into continuous spans. Pre-stressing cables were tensioned inside the girders to improve load capacity and structural stability. After the main structural work was finished, the project moved into the deck finishing stage. The deck slab concrete was poured onto the formwork system, then covered with an asphalt layer to create the traffic surface. Supporting elements such as guardrails, median barriers, lighting, and drainage systems were installed in full coordination. Before being opened to traffic, the bridge underwent load testing by placing multiple heavy trucks across the entire structure. Sensor systems were used to measure deformation and verify the load-bearing performance of the bridge. The results showed that the structure fully met all technical and safety requirements. Since entering service, Vasco da Gama Bridge has significantly reduced pressure on Lisbon's transportation network. Traffic flow has been distributed more efficiently, travel times have decreased, and freight transport costs have been optimized. In addition, the bridge has played an important role in promoting the socio-economic development of eastern Lisbon, enabling urban expansion and strengthening national logistics capacity. Vasco da Gama Bridge is not only a massive transportation structure, but also a testament to advanced design and construction capability under highly complex natural conditions. It stands as a prime example of how transportation infrastructure can solve long-standing challenges and create sustainable development momentum for an entire nation.